So please everyone welcome Dr. Ramalho.
Thank you very much. I'm always glad to be here at USF. It's actually the alma mater of my daughter, one of my daughters. And I'm here to, on behalf of both the Florida West Coast section of the Signal Processing and the Communications Society, where I'm the chair. But we also have an IEEE Communications Society, also on West Coast, that we're co-sponsoring this meeting with. And lastly, but not at all least, is the USF student branch chapter of the IEEE Communications Society. And I thank them greatly for having me, inviting me here today to talk to you about crypto mechanics and DeFi for computer science engineers. The first thing I need to get out of the way, and I'll get it out of the way, inevitably somebody asks me about the value of crypto or Bitcoin or Ethereum. I really don't have fantastic knowledge on that, so this is a disclaimer. This talk is primarily about blockchain mechanics, operation, and theory. It's not intended to provide any guidance towards crypto or its value, or to render any opinion or guidance on how it's going to be regulated in the future, and it is going to be more tightly regulated in the future, or any guidance about how you could exploit this to your own ends. So this is my opinion only. Use it as your own, but I do plan to give you science and technology and computer science examples of how all of this works. So the objectives today are: what makes Bitcoin so special? Some software cryptographic advances that enabled the cryptocurrencies. Software advances that enable what I'll define later on as decentralized finance, which is basically adding smart contracts and virtual machines to some existing blockchain technology. And then we'll close about how crypto is mined, minted and mined, and how it can be held. So that will be an interesting thing, because most people say, yeah, I own crypto. I find out that they really don't own crypto. We'll get to that a little bit later. So my objectives here with you today is to go over blockchain cryptocurrency essentials, the fundamentals of blockchain, and the 3 essential technologies for blockchain. We'll talk about a deep dive into crypto blockchain basics. You'll know everything that there is to know, almost everything there is to know about Bitcoin version 2 in this process, and you'll learn a little bit about Ethereum virtual machines and smart contracts. Key to blockchain, as you find out soon, is the consensus algorithm, and we'll learn about the 2 dominant ones at work here in the cryptocurrency realm today, being proof of work and proof of stake. And then I'm going to debunk some widely held beliefs about crypto. Fundamentally, what I read in the journal papers just really set me off. So we're going to get the real knowledge about how all this stuff works. So let's talk about blockchain fundamentals and the types of blockchains and some common misconceptions. Well, what are blockchains? Blockchains are software-defined data structures in which blocks of data are created via standardized structure. Here I show a header and a payload, where validated transactions, we'll talk about that, and some other state are recorded in a given block. Each block is connected or tied or referenced, generally with a 256-bit identifier, to the previous block. And you keep on doing this and they will form a chain. All of this stuff will become very clear in a little bit. Consensus algorithms are to validate the transactions within the payload. Some of these binders may in fact be opportunistically nefarious or otherwise bad actors. So we're going to have to protect against that. We're going to validate all summary information in the block's header. We're going to determine the active chain and multiple possibilities. We'll talk about that. And we're going to protect against malicious participants. But this is an irreversible set of blocks in an ever-increasing chain. So why don't I get over with 2 misconceptions about Bitcoin, cryptocurrencies, and blockchain. The first is that my nephew does this all the time. Oh, the blockchain is just like a database. It's not. In fact, you will fail my course if you ever say that. So blockchain is a shared immutable ledger that facilitates recording of transactions and assets, and optionally, as we'll learn out later, smart contracts. Anything of value can be tracked or traded on a blockchain network. There's this talk of real world assets that are tokenized and then put on blockchains. Those are NFTs. Those are mortgage deeds. Those are ownerships of song rights. It could be almost anything, but they call them RWAs. So if you ever hear cryptocurrency guys say RWAs, that's what he's talking about. The key blockchain elements are a distributed ledger technology. This ledger, lots of nodes have entire copies of the entire blockchain. It's a distributed ledger with immutable records. What that means is that once you put a record on a blockchain, no participant, I'll talk about what a participant is later, can tamper with the transactions after they've been invalidated and recorded on the blockchain. That means that if you're using this for financial purposes and there's an error in your transaction, you cannot reverse it. But you could put another transaction that effectively reverses it. It's also immutable. And everybody in the world will see the bad transaction and how you reversed it. This is a key transparency concept about blockchains. And and there's another key element is smart contracts, and we'll get into this later on. But the key point here is I want you to learn that blockchain is not a database. It's a distributed, immutable ledger. The other thing that I hear a lot about blockchain is, oh, blockchain is crypto. Crypto is one application of blockchain. The application involves a public permissionless blockchain. That means it's out in the open, permissionless. Anybody can join. It's a part of the blockchain, and Bitcoin really brought that to everybody's knowledge. But that's not the only kind of blockchain. There are just the opposite of that, where they're private permissioned blockchain uses. So for example, if you are Samsung and you make refrigerators, and their components in the refrigerators are compressors, and inside the compressors are motors, and inside the motors there might be armatures or washers or other things that you deal with in electrical engineering. If all of your component suppliers agree to write down the provenance of all of those things, anybody at a later time when the compressor fails can find out where all the parts came from, where they were manufactured. Nobody could change that data. Nobody could fudge around with that data. And so there's lots of other uses for blockchain, private permission blockchains. There are also federated blockchains, blockchains that multiple organizations can use. Let's say you're a state and you've got lots of counties. And within the counties, you've got police and fire, and you've got deed recording and court clerks. All these people can participate in this blockchain that everybody sees, but not everybody can add to. So, and lastly, there are things called hybrid that are hybrid of all the above. What we're going to talk about today is what most students are interested in. They're interested in cryptocurrencies. So those are public, permissionless blockchains for the most part. There's a couple of exceptions for them. So don't tell me blockchain is equal to a database, and don't tell me that blockchain equals crypto. Crypto is one very important use of blockchain. So we're going to talk about public permissionless blockchains, about cryptocurrencies, and then foundational DeFi concepts. So before I teach you how Bitcoin works and how Ethereum works in a little bit less detail, we need to talk about essential technologies. One is consensus algorithms. In other words, random number generators. And the last one is cryptographic hashes. And if I was here for another hour or so, we'd go to digital signing and public key encryption and other topics. But we don't have time for that. So the consensus algorithms for public permissionless blockchains. Their aim is to produce this immutable ledger, distributed ledger, where some of the participants may be offline. Some of them may be nefarious. Some of them may produce inaccurate results. So there's a field in computer science has been around for about 30 years about fault-tolerant computing. Does anybody know what a Byzantine fault-tolerant network is? If you're more master's students, I see more hands raised. That's a typical one. So they're using distributed computing and blockchains to arrive at a state of a network where you've got lots of networks. Some of them may be offline, some of them may be nefarious, but yet you want to come to a definitive conclusion as to the data that you want to put on the blockchain. It turns out that there are many algorithms for this. We're going to talk mostly about proof of work and proof of stake, but just know that there are plenty of others, and I'll bring up some of them as we go through the talk. Random number generators. Sounds like a boring topic, but it turns out that building a really good random number generator is hard. Thankfully, in the late 1980s, 1990s, most of this stuff was solved. In computer science, you're generally using it for key generation for signing and verification purposes. We won't take a deep dive in that. It's also used in salts. But the thing that we're using it for mostly today is randomly choosing things, and I'll tell you what those things are later on. But they're basically choosing the next validator. So why don't we look at one of these cryptographically secure pseudo-random number generators. This guy has an n-bit output, which can represent numbers, if you think about it, as unsigned integers from 0 to 2 to the n minus 1. You give it a seed, and then you hit a clock. Keep on clocking the numbers. And then the output follows a certain distribution, or PDF, whereby you get a uniform PDF. This is a very important thing. In fact, we use this in cryptocurrencies, and we'll show later on. If you want to make a non-uniform PDF, you can actually put a mapping behind there. I don't need to talk too much about that today. But the interesting issues for blockchains is that we want to create random numbers using code that everybody has. So every node should be able to predict what the next value is. So it sounds like there's opportunity for nefarious behavior there, and there is. We're going to show you how we thwart that later on. For a given seed, how well does the output match the PDF? That's been solved. And for a given sequence, for a given seed, every time you clock, the output is identical. Yet for consensus, we need random seeds to using deterministic hardware. I'm wondering if I can get this. So one way to solve this last problem, and that we need lots of different nodes to come up with the same random number sequence in a way that no one of those nodes can predict. So we're going to go through that in a little bit. Okay, what did this just stop? We may need to do it this way from now on. Okay, so the other technology that we need is cryptographic hash functions. Now, most people know what they are. Hand raise if you know what a cryptographic hash function is. I'm not going to ask you for the definition. I just want to know if you know what they are. So there's plenty used. The one that's used in Bitcoin is SHA-256, which you take a input of arbitrary length, you put it through this hash function, and it always puts out a fixed length output. In this case, for SHA-256, it's 256. It always puts out independent of the input. But the interesting thing about a hash function is that if I take hello world and I put it through this hash, you'll get this 250 bits printed in hexadecimal result. If I put as the input hello world, the capital V and the capital W in ASCII coding is only 1 bit different. Yet you put it in the hash and all of these bits look relatively independent of the ones before. And that's called the avalanche effect in hash functions. Two very similar things, you just change a small little bit and suddenly the hash value entirely changes. We use this a lot. In fact, if I were to name this, I'd say cryptocurrencies is hashes gone wild. The class of one-way functions where it's very easy to go this way and it will always produce the same result for the same input. But think about a 256-bit result. That's 256 possibilities. Right? It's virtually impossible to go the other way. So the other thing that we use hash functions are is to concatenate inputs to the hash function. So over here I show a convention where I'm putting some arbitrary input data 1 here, and I'm concatenating it with input data 2, I'm putting in a hash. It's always going to come out with a 256-bit result that looks different than either the hash of the first data or the hash of the second data. It looks completely different than the hashes of either one of those individually. I change the concatenation in different order. I put input data 2 first and then input data 1. I put it through the hash. Well, you said, Michael, if you change any little thing and you end up with a different hash. And in fact, you do end up with a different hash that looks different than either one of the inputs or the previous input. So hashes is a very important property, and we use it a lot. In cryptocurrency, they use the plus function for that. This looks like vector addition to a lot of electrical engineers. I want to let you know that that's not what I'm saying here when they use the plus the getting overcalled, apologize. And this concatenation property is not used often in cryptocurrency. They use it's used a little bit. So let's pretend that we're building a cryptographic block. We're building Bitcoin blocks. And we've got lots of transactions. We really haven't told about transactions that have their signs. But we put them in blocks and we hash those blocks. And we have 4 such here. We hash each block individually. We get the hash of the data blocks. Now you could take this hash and this hash, concatenate them, and you end up with another hash. And like you do the same on the other side. You take this hash and end up with the top hash. The interesting thing about that is anything that changes in any of these data blocks is going to change the hash immediately before it, which is going to change that hash, which is going to change that hash. And in fact, we call the topmost root of such a hash tree structure the Merkle root. And here we just show that there are 8 data blocks. And the good thing about this is you could verify a transaction here by only progressing order log to n of the elements instead of all of the blocks. So that's a pretty important property of hashing. And any data under the top hash, called the Merkle root here, changes. Now, why did I go through all that? Well, we're going to talk about Merkle roots in a little bit. So why don't we talk about blockchain by example? This is where you're going to know everything that you need to know. Blockchain V2. You will know that 90% of the stuff that you read about it in journal articles is in fact wrong. And we're going to show you why that is. We'll talk a little bit how Ethereum was built by showing how it's built upon the foundation of Bitcoin. And then we'll talk a little bit about virtual contacts, virtual machines, and smart contracts, which is really Ethereum's innovation to cryptocurrency. So let's go down to where it all started, which is incredibly new. It started in 2008 with some guy named Satoshi Nakamoto. It turns out that the Satoshi is reused for the unit of Bitcoin, and Nakamoto is also reused in its naming its consensus algorithm, and we'll get to that in a little bit. But this was the original problem to solve. The original problem to solve was an electronic payment system based on cryptographic proof instead of trust, allowing any 2 willing parties to transact directly with each other without the need of a trusted third party, like a bank, like a Western Union, like a Venmo, or any of those. So the original intent was not to be an investment. Nothing in his original paper said that this was an investment. I'm known for that. And although you don't need to trust any intermediate third party, you do need to trust the code that's running in the blockchain. And that's something that lots of people overlook when talking about Web3 and DeFi and cryptocurrencies. The first Bitcoin client was in 2009, which really wasn't all that long ago. And we learned that every block, and they're generated once every 10 minutes on average, Bitcoin, and the first epoch, which is about 4 years, generated 50 Bitcoins every 10 minutes. It turns out that the first commercial transaction was 2 Papa John pizzas, 10,000 Bitcoins. And that's worth about $250 million today. Those are some expensive pizzas. They are not in the back room. Okay. So today we'll talk about blockchain consensus algorithms, not necessarily in the process of individually validated transactions. So listen up. This is the part where you're going to learn almost everything about Bitcoin version 2. And the 2 things that you don't know, you'll learn in a little bit after that. So here's Bitcoin. Starts at Genesis block at height 0, and they keep on tying to one another. I said they tie to one another by means of a pointer. You can talk about that. I'm talking to computer scientists here. That pointer ends up being special. So here heights 0. I'm going to look at this heights 2077, 314, 15, and 16. And tunnel in on this one. So in every Bitcoin block, you'll have a bunch of transactions. Then I'm going to talk about, remember these 2 things, difficulty and nuance. I'm going to explain them later. They're the key to Bitcoin. But the first thing you know is that I can take all these transactions, put them in blocks, keep on hashing them together and end up with a Merkle root. Guess what? There's a Merkle root in the header of the Bitcoin. That's the reason why I went over that. And there are other things that just are trivial: size of the block, the version, the Unix time. The only thing here that I haven't talked about is really this previous block hash, and we'll get to that in a second. But if I concatenate everything that's in the header, is everything that's not in the transaction, I'll end up with a block header, and this is the hash of the block header. The first thing you should say to me is, Dr. Ramalho, that doesn't look random. There are a bunch of zeros in the front of that hash. How could that be? You just told me that you take stuff and it takes the hash and it puts out something that looks random. Well, it turns out there's a reason for that. We're going to get into that. And that's the magic of Bitcoin that isn't reported in a lot of the trade journalism about this. So this has a block header. Likewise, the previous block had a block header. You can't read it here, but actually that block header is put into this block. So if you follow me, this block is referring to that block. If anything changes in this block header is going to be wrong. Likewise, if anything changed in block height 0, that hash, the Merkle root in that block would have been changed. If the Merkle root ever changes in the header, then that block header hash is changed. So you find out that everything from this block down all the way to 0 cannot change. Otherwise, you've broken this chain. And that is really the element that is the chaining mechanism in Bitcoin, this previous block hash. And notice the block height isn't stored anywhere. It turns out in a later version of Bitcoin it actually is, but not for the purpose of chaining together the blocks. So the whole key of this, I've told you everything except for these two fields, this difficulty and nonce. Why don't I get to where those come from and how we deal with them? So Bitcoin uses something that's called proof of work consensus. Fundamentally, it means the more ability you have to generate hashes, the more likely you are to produce the next block. We're going to talk about that in a minute. That is, in fact, the genius of Bitcoin. It's also its downfall. So we'll talk about the downfall of Bitcoin. So proof of work consensus. You guessed it. Cryptocurrency, I said, our hash has gone wild. Well, Bitcoin's computationally intensive puzzle. You may have heard that Bitcoin, it set all these miners out and they solve a computationally intensive puzzle. They do no such thing. They actually try to solve a cryptographic hash. In this case, to have a cryptographic hash whose value, when you look at it as a UNT 256, is low. That's the reason why there are a bunch of zeros in those block headers. View that block header hash as a UNT 256, the very first position is 2 to the 256, right? So you got a bunch of zeros, so that value, whatever it is low. We're going to talk about how low that value is. In this case, solving the puzzles that require the hash result to be below a target value. We'll talk about the target value related to difficulty. The only known way to solve this puzzle is not to solve it, is to keep on guessing. Eventually, you'll guess some input to this hash that will have a value that has a bunch of zeros in the front. That's as simple as it gets. One miner will be typically all the miners, and we'll talk about how many miners they are and what the total hash rate is. One miner will come up, my goodness, I chose something that has that many zeros in the front. This value is, the hash result is really low. He'll advertise that block to everybody else, and everybody else will be able to verify that, in fact, everything he did, everything that node did was okay. Once a solution is found, it's not necessarily unique. The winning miner advertise it. All the other miners can verify it. All the other miners say, okay, you guessed it first. I'm moving on to the next block. I'm going to show you how this works in detail. So the first thing we're going to do is to show you that, in fact, this is how Bitcoin works. We're going to do what all good engineers and computer scientists do. We're going to assume the form of the solution is simple, and then will make the real solution. We're going to make an assumption right now that it's a power of 2 to make my point. So I said concatenation is used a lot of times in cryptocurrencies as input to hashes. So we have to look at the block header and we have to hash it. And that's the thing that we saw had lots of zeros in front. So I just have this notationally as the block header without the nonce plus the nonce. So computer scientists, you know what a nonce is? Or for signing or for cryptographic purposes, it's a number used once. It doesn't mean anything to me when I heard it first, but what will happen is we're going to increment this nonce field from 0 to 1 to 2 to 3. It's going to be a part of the thing that we put into the hash and we're going to get a result. But we know that before that using different notches in the hash will produce seemingly random results. Remember the whole world and the whole world? It was one bit different, but the hash outputs looked completely different. So if I asked you the following question, I'm going to try nonce value of 0, and I'm going to try nonce value of 1, I'm going to do nonce value of 2. How many nonces do I have to try such that the output has a 0 as its first bit, and I don't really care the rest of them? Well, that's an easy problem. You just say, Michael, you said it was random, right? And so there's a 50% possibility that that very first location will be a 0. And there's a 50% chance that that first bit will be a 1, and you'd be exactly right. In that case, you say, well, I want a result that's less than 2 to the 255th. So there's a 50% probability. But let's say I ask you a different question. I'll say, how many tries on average do I need to try to get the first bit equal to 0? Well, if you know your probabilities really well, this is not a trick question. It's actually an easy one. Lots of probability questions come out with answers that I can't guess. But it turns out that the probability distribution of expert-early trials need to get one success. In this case, the success is defined as a 0 in the first bit. Is a geometric distribution where the distribution is 1 over p. So on average, we expect to need 2 trials, 1 over 1/2. So we get lucky, we get the 0 on the first try, get 2, but you know how probabilities work. The half plus the quarter plus the 8 plus the 16th, that whole sum will equal 1. Now, because I'm going to use that later on. So there's a key result. If you want to try nonces 0, 1, 2, 3, and you know the output of the hash is random, and you want the result to be a power of 2, you want k zeros followed by a bunch of stuff that I don't care about. How many nonces do you have to try on average? And the answer is 1 over p. Well, p is equal to 1 over 2k. So it turns out you need 2k trials to obtain this result on average. So if I want 2 zeros, I need to try 4 times on average. I keep getting unlucky, and have to try a lot more. 3, I need 8. 4, I need 16. You know how to count in powers of 2. So I'm going to repeat that important result at the top of the slide. If I want to just keep on hashing this block header, lots is 1, 0, 1, 2, 3. How many do I have to try to get exactly k zeros on average? Now let's talk about Bitcoin. Bitcoin's goal is to produce a block once every 10 minutes. If we knew the total hash rate of all the miners that are working on Bitcoin, and let's say it's x per second, that is 600x per 10 minutes, 60 seconds in a minute, 10 minutes. And we wanted to say, if we were limiting the hash results of that form, can we find k to produce a block every 10 minutes? We said 2k, 600x. We take log base 2 of that, and you get the answer. So this is 2001. This is a graph of tera hashes per second, which is 10 to the 13 hashes each and every second. And this is 2021. It turns out that there was a China outlawed Bitcoin mining in the country. That's the reason why the hash rate went down. But then they took that equipment and put it elsewhere, and the hash rate went back up. So anyway, that's 200 million petahashes per second is 2 times 10 to the 21. So let's do that math. The approximate hash rate in April was that. So log base 2 of that quantity is using 79 leading zeros that you need in the block header hash. Likewise, if we look at this point in time, you need 78. The interesting thing is you can go back on the block. There's a block explorer. I'll show you the URL for that later on. And look up any block in Bitcoin that's ever been minted. And actually look up the header hash of any block that's ever been minted. And it turns out that this one on April 4th had 19 hexadecimal zeros. Each one of those counts as 4 bits. And then this one is a 2, so you got 2 more zeros up there. So it actually had 78 leading zeros. So they found a nonce that when they concatenated with everything else and they hashed it, instead of getting us a randomly looking thing, they were actually looking for something that had that many zeros in it. But that is an incredible number. That number in hashes per second is like more than the grains of sand in all the world's known beaches. I mean, and that happens every single second. So, Michael, that's a lot of computers crunching on things. And yes, we'll talk about that. If you actually want to explore this for homework, you can actually go to this demo site that has transactions, and you click mine, and it will increase the nonce 0, 1, 2, 3 until it gets something that has the form of 4 zeros. 4 hexadecimal zeros is 2 to the 16th. On average, you should expect to find it within 65,000 tries. This one actually took longer. This miner over here has the same transactions in a different order. So he's working on a different problem. That Merkle root is different for this miner than that miner, and he has the same problem. You click mine, it only took him 23,000 trials. So the interesting thing here is that you got all these miners, you got transactions, they group them into a body, they calculated a Merkle root, and they keep on trying nonsense in other fields to get the result of the hash that happen to be a very small, relatively small number in the space of 256. So you can create your own blockchain if you want that. Okay, so if you remember in the Bitcoin version 2 block header, I said this is nonce. Now you know what the nonce is for, but then this is difficulty thing. So we're going to talk a little bit about this difficulty thing. And the target in Bitcoin isn't what I was just talking about. It didn't have to be a power of 2. It just has to be a value. I showed you the power of 2 to show you that's exactly what they're doing there approximately. So within a power of 2, that's exactly what Bitcoin's doing with historical data. So what Bitcoin actually does is it generates a target value. It adjusts this value once every 14 days, every 2 weeks. Every 2 weeks, at 10 minutes a block, on 6 10-minute periods per hour times 24 days times 14 days is 2016 blocks per 2 weeks approximately. And it compares that sum. Each block took 10 minutes. It should have taken that many minutes to produce that many blocks. And then it adjusts this target value up or down and make the result for the next 2 weeks closer to 10 minutes. So if on average they were doing 11 minutes per block, they'll make it a little bit easier the next epoch. So Bitcoin difficulty adjustment is an adaptive control system. That's what electrical engineers would call it, maybe not computer scientists. But anyway, the game is rigged so that they're adjusting these values to make sure that Bitcoin produces a block once every 10 minutes. And they do that by adjusting this target level. But it's independent of how many miners are working on the solution. If you solve sooner than 10 minutes, make the following solutions harder. That is, make the target number smaller. If it takes longer than 10 minutes, make the following solutions easier. Increase the number so that it's easier to get to. So, again, 2021. Every one of these lines, there's 265 of them, are the average time to mint a block during that day. Every 2 weeks, an average is calculated on how long it took for the average over the 14 days for a block to be minted. It's the same period of time is 2021. Doing that SES1 shutdown where they closed down the miners, they shut down the miners, hash rate went down. It took longer times to develop those solutions, but the adaptive system worked. Came down and it's still producing blocks once every 10 minutes. So here are the details. The target value is derived from something that's called the difficulty. Difficulty relates the target value to that used in the Genesis block, which is block number 0. It is the difficulty level and not the target. I don't know why they didn't report the target. Make my lectures a little bit easier. It's a difficulty level that's in the header, and it's fixed for 2 weeks. So now you know all the fields there. You can actually go to the Blockchain Explorer. You can look at the difficulty and find out that that difficulty field stays the same for 2 weeks. And now you know all the fields in the Bitcoin version 2 header. So the question I get asked is, well, how much does it cost to mine? So let me just assume that the total pie here is the total hash power of all the miners in the world. Now let's say miner 1 has 10% of it, just to make the problem easier. Let's say he doubles his hash power, which is usually doubling the number of GPUs he has. Well, now the pie got larger, so he hasn't quite doubled his share of the total hash power. He has 18% of the hash power. So he almost doubles his chances of producing a block by doubling his hash power. Remember, all this stuff is probabilistic. I got more hash power. I have more chances of guessing that something that meets that criteria. Well, you say, well, Michael, it works that way. What happens if everybody doubles their hash power? Well, it turns out if everybody doubles their hash power, miner 1's share of it is still 10%. This is a probabilistic thing. He hasn't changed his chances of winning at all. But now his costs have doubled. See, Michael, if it works that way, why can't it work the other way? What happens if all miners collude to half their capacity? It's hard to get these kind of people to collude to half their capacity when it's in their best interest to keep the system to go a little bit higher. But it does work the other way around. So this is Bitcoin's tragedy of the commons. The lowest cost miners always have an incentive to increase their hash power. That is really bad thing, because it just means that this is an arms race for hash power. And that's where you get those tetrahashes per second from. One thing's really clear, though, for the economics of Bitcoin is that if mining cost for a given miner is greater than their profit, where your profit is defined as the Bitcoin market price, you see on CNBC, minus the mining cost, the miner will stop mining. But what happens to the hardware? We'll talk a little bit about this later on, but the hardware generally gets redeployed elsewhere on something that's called altcoins, which are coins that are very similar to Bitcoin. You may have heard of Dogecoin, those sorts of things. As you learn, though, anybody who leaves the Bitcoin ecosystem of hashing, the difficulty is going to be adapted anyway, and they're still going to be producing blocks every 10 minutes. So the market price of Bitcoin has a significant effect on the profitability of mining. But anybody who's taken Eco 101 knows that things are generally, market prices are a function of supply and demand. Demand, who knows? People want Bitcoin. Supply is another story. So we're going to talk later on about how Bitcoin supply works, and some of the other cryptocurrencies supply works. But before we get there, I haven't really explained how this consensus works. You've got all these miners emitting blocks. The first thing they do is they put together transactions. They verify that all of them have been signed correctly. They make the Merkle root. They make their header. They play with nonsense to come up with this header value that's low. So how does this actually work in a real system? The real system is, let me just assume here, Bitcoin assumed that these miners were geographically dispersed. And two people may actually come up with a solution, one that's valid, at about the same time. How do you resolve this in Bitcoin? It's called conflict resolution. So Bitcoin, the miners always build on the longest chain. They get the new block when they're first to find the hash value, the target value. Given network delays, I gotta get over this call. Two or more miners may solve the hash problem at the same time. Again, depending upon propagation, some miners may see this as the longest chain, and some others may see the other one as being the longer chain. The majority of the time, most of the miners will work off of one of the forks, in which case the next block is mostly minted from this fork over here. I thought B and C will do it, and this will become the longest chain. Everybody who's working on A will give up. However, the worst case is half the hash power gets working on something that's off of A, half of it is off of B. You look at the statistics involved. It turns out it's still probabilistically probabilistically, one of these forks will be the longest, not too much time. In the literature, that's called the time to finality. So the genius of what Satoshi Nakamoto did was said, I'm going to give you, you don't have to ask for permission. You could all just mine and whatever you want. You could see the entire blockchain database, put it on your machine, put it on your GPUs, run it in your dorm rooms or apartments, and be a part of this system. That's wonderful. Even if you've got a nasty node, right, you're going to be found out. And nobody can cheat the system because everybody has access to the hash function and can prove whether or not you've in fact created a valid next block. Lastly, if there was a transaction on A, the miners that make these blocks pull transactions from something called a mempool. And it's entirely possible that some transactions made it onto B that didn't make it on B or in A. They'll be reintroduced in the future. So this is called Nakamoto consensus. It's a natural fit for open permissionless system where any node can join at any time. But I talked about those tetra hashes per second. If you get that NVIDIA GPU and you put it in there, you're competing with this. You're competing with people that have racks upon racks upon racks of devices like this. This has gone down by a factor of 2 since I last gave it installed, by the way. This is a 11 hashes per second, but 1,200 watts for $300 on Amazon. You're competing with all of this, and all of this, and all of this. I have a slide that I took out of this deck. Basically, your GPU is never enough. So what you do, well, really, you're part of a hash pool, and you generally join that, and you'll get paid based on a relatively low chance that your GPU will actually find the solution before anyone else. So there are stuff, there's code that you can download to your computer to actually do this. Just don't fool yourself and think that actually your GPU is ever going to produce a block. The odds are overwhelmingly against. So now you've learned that Bitcoin mining isn't mining. When you mine for something like gold, you go to where the gold is, right? And it's not puzzle solving. You're not solving a puzzle. You know, any intelligent person would not try a corner piece in the middle of a puzzle. Each one of these devices is randomly guessing. Randomly guessing. There's nothing honorable about minting Bitcoin. It's really the idiocy of random digging. This footnote doesn't have a sense of smell. And it's so bad that 99.99 actually % of the energy used in the Bitcoin ecosystem is used for trying to guess a nonce that will produce a hash value that doesn't look random. It looks like a bunch of zeros in front of a very low number. That's insane. Using 99.9% of the power, not to build blocks. So it consumes over 2 times the power it needs in Switzerland. And there's got to be a more efficient way of doing this because this is unsustainable. There's got to be a more ESG friendly way to do that. So whenever anybody says that, Bitcoin's solving a computationally intensive puzzle, you could go and say, because it's really not true. So engineers do things like when they want to demonstrate something, they assume the form of an answer is power of 2. We're going to do something similar here. Statistically, we know the answer if we simplify the problem. Let's say we have n minor nodes. And we know that each has identical processing power. We're simplifying the problem. We're going to desimplify it a little bit. And we know that every 10 minutes, one of those CPUs is going to find the solution to this cryptographic puzzle. We just don't know which one a priori. So the natural question is, can't we just pick one? Well, I could certainly do that. I could go to the Dr. Ramalho benevolent random choosing machine. The problem is nobody's going to trust my code because it hasn't been rigorously vetted across the whole world. Why would somebody trust me? The whole thing about Bitcoin is that it was based on something that's called the Decentralized Autonomous Organization, where they don't count on any governments, they don't trust any formal regulatory structure. So they're definitely not going to choose me. You said you mentioned these cryptographically secure pseudo-random number generators earlier that you must be wanting to use them sometime. And yes, I am using them. So the whole question here is that can the seed provide the needed randomness? Everybody has the same number generator. If they all given the same seed, they all know the same sequence. But now that the problem reduces to, well, how do I choose the seed? Did I mention to you that Bitcoin and cryptocurrency is hashes gone wild? Of course, they'll solve this problem by using another hash. So what they'll do is that they'll say, okay, there are n miners. They'll all register a secret. They'll concatenate them together, and that will generate a seed that is indeed truly random. One problem with that. If the last person holds back all the other seeds, they know what their seed, what their secret will generate that seed. That's called grinding. Unfortunately, we have other uses for that word. But, so that fails because somebody who holds back and waits to the last minute can actually affect the outcome. So did I say that cryptocurrencies is hashes gone wild? I did say that, right? Well, I'm going to solve this problem by the step one is not giving everybody your secret, but a hash of your secret. The hash, people can't go the other way. They can't figure out what your secret is from the hash. Then, after you enroll, then you send in your secret. Every other node can say yes. In fact, S1 hash produces H1. So this works. It's like, wow. So you verify the previous hash, and then now step 3, you can't see it's off the screen. Then you take the secrets, which nobody could gain anymore. You get a seed, and now everyone knows what the hashes are, know what the secrets are, knows what the final hash is, knows what the seed is, which they could not have predicted. No one of those nodes could have predicted it. And now it knows what the sequence of numbers that this pseudo-random number generator will produce. So it turns out that this was used, and I think it still is used in Ethereum. But that is a scheme that in fact works. So you don't have to have tens or hundreds of thousands of tetrahashes per second, guessing at hashes like they do in Bitcoin. You can now come up with a probabilistic way to choose who gets to create the next block. And that brings us to the next section of this talk, which is called something that's called proof of stake. I don't like that term, but I'm going to use it, so I will use it. It was first used by a cryptocurrency called Peercoin. And fundamentally it means the more native currency of that blockchain that you staked. What that means is that let's say I'm a part of Peercoin's system and I have 100,000 Peercoin. I'm not going to use a transaction 100,000 Peercoin. I'm going to give it to a node. I'm going to promise not to use it. There are safeguards that actually make me not be able to. The node that has more stake behind it, more people that have locked up their currency behind it, the greater chance that they'll be chosen. And consensus is based on economic rewards and penalties. We're going to talk about an example of this. This right now sounds very abstract to you, but the main thing is that it's using 99.99% less power than Bitcoin because you don't have to do a lot of wasteful guessing. Somebody just gets randomly chosen, but everybody knows the way that it's randomly chosen. All these people use it, including Ethereum 2.0, and we'll talk about the differences of it. So we just showed that you could choose 1 out of n possible CPUs, create the next block. And since 99.9% of Bitcoin's energy was wasteful guessing, how do we choose it? Well, it turns out that this is the loose definition of proof of stake. There are n entities. They call them validators. They don't call them miners in theory, or stakers. Any one of the n can be probabilistically chosen as the creator of the next block. The probability that any one validator is going to be chosen can be different than the other as long as the probabilities end up in one. But cryptographically secure random number generators actually guarantee that. In pure proof of stake, the probability of being chosen is a function of how much your stake is relative to the total stake. All these nodes are set aside money that can't be used. You sum all of that, and then you find out how much this node is staked, and that's the probability of you being chosen. And again, this is pure proof of stake. It's not built upon the premise of solving a cryptographic problem. However, particularly in the early days, there are more opportunities for collusion and other attacks. Remember, I had to register and I had to send in these secrets. There's more communication that actually has to happen in a proof of stake system relative to what Bitcoin did and the genius of Bitcoin. So if you want to know more about proof of stake, you actually look up Algorand. It has pure proof of stake. The more money that you set aside in your node increases the chances of your node being chosen for the one to produce the next block. However, you can use any other criteria you want. You can use age, you can use the penalty for being offline, almost anything you can think of, you can modify the probabilities of being chosen. And in fact, that is the difference between most of the other proof of stake based cryptocurrencies. They all follow the same basic principle that you stake some money, you stake the cryptocurrency of the blockchain that you're using. And you're going to give me the rope? We're 4:30, right?
No, look, just taking pictures.
Okay. So this is the, there are as many variations as you could think of criteria for modifying the probabilities. If you're a really bad guy, there's this that will lower your probability of being chosen. So I like to use probabilistic validator selection for these schemes, but I haven't written a book yet, so I don't get to call them something other than proof of stake. So why don't we talk a little bit about hygiene? We talked about Bitcoin and this Nakamoto consensus. There is no known way to game the system. Nobody's broken that hash to figure out special things that you can put as inputs to it that will cause the outputs to be something that you want. The winning miner is awarded a block reward for being lucky, and also transaction fees for transactions with this block. We didn't really talk too much about anything about that. And some power limits have coin limits. And once these limits are met, we'll only receive transaction fees. We'll talk about that in a little bit when we talk about Bitcoin money supply. Proof of stake, on the other hand, uses an economics-based consensus algorithm. The validator is chosen, is awarded a block reward. It passes most, when it does win the chance of getting a block, it gets a block award. But there are people that gave it staking money, and generally they'll pass the award to the staking participants as rewards. We're going to talk a little bit about transaction and gas fees when I talk about Ethereum. And there are other things. Slashing is a penalty mechanism. So there's lots of other things that you have to build into proof of because it's not as clean theoretically as Bitcoin. You've got these pluses and minuses. So if proof of work is so wasteful, those hundreds of tetahashes per second, are there alternatives? And it turns out that Ethereum actually did this. It went from proof of work in 1.0 to proof of stake, and it happened very recently, September of last year. In fact, I gave a version of this talk before it happened. And they did, in fact, reduce power consumption by 99%. I'm going to skip over those next points, except to say that that blockchain is very much more controlled than Bitcoin's miners. In fact, Binance CEO once stopped, and they has his own cryptocurrency. Actually, asked all his validators to stop a smart contract because the contract had a security leak in it. You could bleed Binance coins out of it. So this one person stopped execution of a smart contract and all of the validator nodes on this network. And that's kind of against this decentralized autonomous organization principles that no one person, no one government, no one entity controls. So we're getting a little bit funky there. So why don't we talk about Ethereum? Ethereum had a proof of work, what they call an execution layer. These blocks were virtually identical to Bitcoin. We'll see the block header on the next slide, and we'll see that it's virtually identical. They actually created a proof of stake chain, probabilistic choosing mechanism, had a rando to it. And they operated alongside of it until a point in time last September, where actually they set off what they called in the journal press a difficulty bomb. You now know what a difficulty bomb is. What they did was they set the target level so low that no one could actually generate a hash with that many zeros in front of it. No, it was theoretically impossible. So it turned out that the proof of work stake stopped at 1 block. The next block could not be produced, and that was their mechanism to stop that. In the meantime, this chain is going along, and it's something. The very next proof of stake chain hide the blocks at that point. So that's what they did. They're not autonomous, major departure from the Bitcoin principle. So here's what the block header looks like. For Ethereum 1.0, that header looks very much similar to Bitcoin. You've got a parent hash, which Bitcoin called the previous block hash. It's got a difficulty field. It's got Merkle roots, just like Bitcoin. You can just think about this header as identical to Bitcoin. At the time of the transition, they started tying things together with this rando value, this cryptographically random secure generator value. But they still incorporated other stuff that looks like Bitcoin, and they reused the field that now had difficulty to put a previous rando in. So the reason why it took so long is they wanted to do a lot of testing. They didn't want to get it to burp and to screw up in this process. It wasn't as crazy as the hype that said it was analogous to changing an engine in mid-flight. You look at this and it's pretty conceptually easy. So no more of these blocks are ever going to be built. You just tie the last one that you had in here. And now you start using what you did use for proof of stake. It's conceptually very easy. But the thing that I want to get across here, I still don't see enough in the literature, is that Ethereum proved that you go from this wasteful proof of work, all these hashing machines, all these miners, and save 99.9% of the power. You have some trade-offs in governance and how the blockchain is made, but Ethereum proved that you could do that. Did Bitcoin do that in the game? I haven't heard anybody talk about it, but it's possible. Ethereum actually proved it. So here's what I want to leave you with. In fact, if the talk ended right now, I'd be happy, because this is the most major thing that I wanted to convey to you. The differences between proof of stake and proof of work, they're in dominantly 90+% of every cryptocurrency that you have out there. The proof of work stuff works on consensus due to the mathematical properties of cryptographic hashes. That's the good part. The bad part is that it's very, very wasteful, incredible waste of electrical power. However, you can still crank up those graphics units in your dorms and actually join it. In fact, we could copy the code. That's what Dogecoin did. We can create a Dr. Sadiq SIM card and make one right after your department head. Right? There's nothing to stop us from doing it any more than Dogecoin was built as a dare by Elon Musk. Proof of stake properties, virtually no power wasted in choosing the next validator. You learn that you send in a hash of your secret. Everybody does the same thing. Then you send in your secret. You shove it into this cryptographic random number generator, and you just go from there. Increased scalability relative to Bitcoin. As a validator, you need to enroll. These things are a little bit harder to do, but the minting costs are practically zero. Trust in the blockchain governance is very, very important. I can easily give another lecture on that. And we'll talk a little bit about these things, but it's really important. This is my complete list slide. There are lots of other forms of blockchain consensus. You've learned about proof of work. You've learned about proof of stake. There are other things like proof of authority. I asked before if anybody knew what Byzantine fault tolerance was. One of the chains from Ava Labs, which is actually from my alma mater, actually uses this, and it's pretty high in market cap. I mean, 18 market cap of all the cryptos is pretty significant. They also have other relations, but the thing that I want to leave you with is that if you want a job in this, it's still early. It's still early innings for this. If you're interested in blockchain, there's lots of innovation. So why don't I talk a little bit about the next major innovation in blockchains, and that's virtual machines and smart contracts. So Bitcoin was basically an alternative to fiat currency, the original problem to solve that I showed you before. But Ethereum is a platform for facilitating contracts with its currency in addition to what Bitcoin did. So Nick Szabo actually coined the phrase smart contract. It basically takes a contract that you normally write out in legalese, but you write it out in code, and you try to make sure that there are no holes in the code, just like lawyers try out holes in their contracts. It's simply a program that runs on the blockchain, and it also has something it adds something to what Bitcoin normally does. Bitcoin normally just tied together blocks of transactions. So what Ethereum does with smart contracts, you predefine a contract, and something happens. Maybe the first of the month happened. Maybe it's a mortgage payment. Maybe stock went over a certain threshold, and you have to sell it because of all stock or something. Whatever that event occurred, it causes execution of some code, some interpreted code, and then there's a settlement. So what Ethereum needed to do was, first of all, build a virtual machine. But also, in addition to transactions, it also had to carry in the blockchain something that's called proof of stake. The important thing is that all parties must trust the contract. And smart contract execution isn't free. It costs something called gas. So let's a slightly deeper deep dive into Ethereum virtual machines. So Ethereum native currency is Ether. A very small version of that is Gwei. And you've got the code. So this is the code that executes the contract. You'll see, and it's interpreted code. So every opcode, this code probably generally gets compiled in this machine language. Every opcode in the machine language costs something to execute. That's how complicated that instruction is. So you go through this and their operations, and you can create local memory, but then there's also memory out here that you might want to instantiate on the blockchain. So external storage costs a lot of gas, plus a lot of this currency, because the stuff you put out here is going to stay out here forever. It's going to be part of the transaction and state on this blockchain forever. Anybody could look at it at another time. modifying external storage on subsequent locations is costly. Also, if you pass this code with not enough gas to actually execute the code, it basically barfs and reverts. Reverts generally means no updates happen on the blockchain. It actually means something a little bit more formal if you look at the code. So the thing is, only use external state when absolutely required, because even talks like this have to have a little bit of humor to them. You have to make sure you pass enough gas. So this is a popular smart contract code. By the way, there is pizza and stuff back there if you get really hungry. This is a interpreted program called Solidity on my Microsoft Visual Code. And this is the contract. This is some sort of voting contract. This looks like any other curly bracket kind of structure for a voter. You'll see that this thing is called address here, so there's a different thing in there. When this code first executes, it executes something that's called a constructor, which basically instantiates on the blockchain, or is going to execute. It's going to instantiate after execution all the state that it wants on the blockchain, so that when it goes away and gets called by some other event or some other thing that causes it to execute again, that state is on the blockchain and it can find it again. Interesting thing about this code, this is the first language I've ever dealt with where the default UID is 256 bits long. Surprise, all these hashes are 256 bits long. All these cryptocurrency addresses are 256 bits. In fact, if you actually put a UID8 and say, listen, I never had more than 64 things, I'm going to use a UID8. You've made a mistake in coding this smart contract, because it has to emulate all those overflow in the UID8 on a native 256-bit machine. So there are some things when you write in this code that, although they'll work, they may cost you an abnormal amount of currency, or they call it gas. It also has interesting things about requires. So as a smart contract comes through and it finds out it requires certain things that they haven't been met, it will also terminate. So, but when it does do that, all the gas fees that have been executed up to that point are actually still consumed. Lastly, although not shown on this example, the smart contract execution can trigger other events and such. And errors. Errors are another important thing to look at what happens on them. So, we're wrapping up. So let me talk about some, I talked about some misconceptions earlier, blockchain doesn't equal database and such like that. I also hear some widely held beliefs in Bitcoin that I want to understand that their beliefs that sometimes aren't true. So the original Bitcoin money supply, and it has not changed, was to generate 50 Bitcoin be awarded for every block during the first 4 years. After that, the next 4 years, the block reward is going to halve. The next 4, it's going to halve. Okay. So every 4 years, there are 210,240 blocks. Bitcoin's reward epoch is almost that. Why did they terminate? Why did they truncate to 240? I don't know. You're going to have to ask Satoshi Nakamoto. All the math in the code would have worked quite fine with 240. So only approximately every 4 years is this change in Bitcoin. So that's the reward for the first epoch is 50 Bitcoin for 210,000 blocks, or 10,500 Bitcoin. So why don't we put this algorithmically? The first 4 years, we generate 10,000, sorry, 10,500,000 Bitcoin. The next 4 years, half of that. Back. Well, we've already looked at this summation, and I said before, what is a half plus a quarter? Of course, it sums to 1. So now you know it's pretty easy math. The Bitcoin limit, the Bitcoin that will ever be generated, is 21 million Bitcoin. That is the limit. So why don't we look about this a little bit closer? The first epoch was 50, the next one's 25, next one's 1250. Right now we're in the epoch that generates for every Bitcoin block that you produce 6.25 Bitcoin. That happens once every 10 minutes. But if you look at the like CDF of this, right? Really 93% of all Bitcoin that will ever be mined, as long as the code doesn't change, that will ever be mined has already been mined. Why don't we look actually at the code that generates this? So I don't know if you guys can see this, but this generates the amount of the block subsidy. The first thing it does is there's an integer truncation of the block height and this parameter, which happens to be the epoch, if you go through the code. So until the block height matches that or above, this truncation is always going to go to 0. And it did on the first epoch. Halvings takes 50 Bitcoin. I don't know if you can see it says 50 point here. Subsidy is that 50 shifted right by the number of halvings. Halvings is 0, it passes 50. The next time when this guy's height, right there, above that, integer truncation, you'll go through these epochs, and the subsidies will keep on halving over time as the blocks keep on getting. But there's one interesting thing that happened here. They said, we run this on 64-bit machines. We should put a caution in here, which, by the way, won't happen for our lifetimes. If you ever if you ever try to do shift rights by more than 64, that's undefined on some machines. So why don't we put a little piece of code in here that says, if you ever try to do that, just set the halvings to 0. We're not going to give you any block subsidy. What's important about this is not this code, but the fact that they introduced the governance of Bitcoin, which is this Decentralized Autonomous Organization. It has structure to it, that has rules that people voted to put that in there. What's to stop some future governance of Bitcoin and change this function and create more Bitcoin? And the answer I'll leave to you. So Bitcoin's design and scarcity is this 21 million, but I say you could change this in the future. And I heard for the first time somebody other than me do this was Jamie Dimon on CNBC 2 weeks ago. But some pretty important people have actually stated it. El Salvador uses Bitcoin as their national currency. The president keeps on talking about 21 million will ever, all that there'll ever be. So, it's really talking about artificial scarcity. Kathy Wood of Ark Investment also talks about artificial scarcity. So I pose the following question to you, which I'm going to actually pose to the USS Business School. Cryptocurrency is a currency and not a commodity and not a security and not a futures contract or a bunch of other things that they say that it could be. Why is a capped Bitcoin supply the right answer? It isn't. I don't know what the right answer is though, right? So Dogecoin has a similar limit. Solana has an interesting thing. They target an inflation rate of 1.5%, which is kind of like a Federal Reserve target. So it's getting closer to what I think is kind of a reasonable solution. But in any case, the supply of the cryptocurrency should have a factor in its potential worth. So we have all this question about how much does it cost to mine Bitcoin, how much is it worth, function of demand and supply. I don't know what the supply will be in the future. So why don't I close, and by the way, Matthias, is there anybody coming in after us? Because I'll just,
No.
I only have like 5 or 10 minutes.
No, you can continue.
You can continue.
No, with the people on Teams, I'm going to go a little bit long too. So one of the things that I've asked a lot is do you really own crypto? It turns out that I don't, because I don't fully understand the value. That's just being frank. I mean, I could have done this with a bunch of my Cisco friends that actually invested $1,000 in a basket of this cryptocurrencies about 7 years ago. I look like a fool. Their investment went up so hard. And anyway, so we're not going to talk about this in detail, but every transaction on the crypto blockchain is actually based on public key cryptography, which involves a public key and a private key. Way most of these things work with crypto, the roles are reversed here. In signing transactions involves your private key. And anybody knowing your public key, which is public, which they can know, can validate, in fact, your transaction. So an entity A wanting to send crypto to entity B needs to use two cryptographic keys. It needs to use his private key for signing it. And it must keep this private, otherwise other people could sign transactions that he didn't make. And public B, entities B public key. Or equivalently, we can go through this. There's the public key, and then there's a couple transformations to actually the Bitcoin address, but there's a one-to-one correspondence between them, so I'm using public key and Bitcoin address somewhat synonymously there. And then anybody wanting to send crypto to entity A, like me, needs to know my public key in addition to its own keys. So there's a mantra in crypto that says, not your keys, not your coin, or not your keys, not your crypto. That is that the blockchain doesn't know you by your Bitcoin address. You don't own. That tricks up people. We're going to take a deep version. Dive in that, because the two ways that crypto is owned is self-custody. You keep track of all these keys. These keys I say people use them before. Or exchange custody, where the blockchain doesn't know you. You go to PayPal, and they will, on your behalf, buy the crypto with their keys. And likewise, when you report it back, they'll convert it back to fiat currency. That's a future date. So why don't we look at this a little bit deeper? You might have heard of wallets, cryptocurrency wallets. In self-custody, you put your keys in your wallet, which is a loose analogy. I mean, I don't have my entire bank account. But you can put it on a USB device. By the way, don't ever run it over or lose it or lose any passcode that you need to access it. The idea there is you only plug it into the machine when you're actually doing the transaction and you use the keys, and then you pull those keys off the internet so you have very little exposure. You can use a paper wallet. Write down the 64 hexadecimal digits to your private key, and you'll be able to do that. But don't lose the piece of paper, or you lose access to your crypto. That's an interesting point. You'll lose the ability to move your crypto. Your crypto will stay on the blockchain forever. Because no one is ever with the 256-bit key going to guess your key and move it. It's going to stay there for as long as that blockchain exists. The other way people do it, and there are a lot of people that do exchange self-custody, is on a centralized exchange. So you could tell Coinbase, I want a self-custody account. They will keep track of your keys. You'll log in with login password, just like you do with the bank. But they will have your keys. You will have, by means of proxy, an address on the blockchain. And you truly, as far as the blockchain is concerned, will own your crypto. I hope that was clear. Exchange custody is the entity owning the crypto, is really the exchange. Has the look and feel of an online brokerage account, Venmo, PayPal, Robinhood, those sorts of things. Your cryptocurrency ownership is really a bookkeeping entity, similar to your local bank. The exchange manages your transactions associated with your account with its keys. You don't have keys. Coinbase stated that in their bankruptcy, if they had one, the crypto that you bought with them in this model, you didn't choose exchange custody, you didn't choose self-custody, you chose exchange custody, can be used to pay their debts. It's an asset they control. There's no SP protection for you. This is the part that most people don't appreciate. For people who bought crypto and FTX, they had a bookkeeping entity. You didn't own. If you were a Coinbase customer and you asked for your self-custody of your own wallet, you had keys on the blockchain. You didn't lose anything. like FDIC, right? And those wallets should be able to be resurrected by federal government, federal and other authorities. Lots of jurisdictions, including Canada, view this as a futures contract. I buy $1,000 worth of Bitcoin. 2 years later, I decide to pull it out. Right? They just give me the value of that Bitcoin on the way out in fiat currency. They're not giving me that. So that's what I mean. It's a futures contract. It's something that I negotiate with you. I give you $1,000, go buy Bitcoin. And by the way, your contract with me is that you'll return the fiat currency value. So sometimes your crypto is insured against loss. I had a friend of mine who got all worried the first time I gave this talk. He used exchange currency. He used Robinhood. It turns out this is an interesting story. But Robinhood actually, I can go into the details. Robinhood actually realizes that Lloyd's of London realizes that Robinhood only has a certain number of its keys exposed at any given point in time, and they monitor what it is that they do and actually insure against loss. So the story here is deal with reputable exchanges. That's the reason why all this governance stuff is becoming important. So I'm going to wrap it up with these slides. Blockchain governance, I mentioned this, Decentralized Autonomous Organization before. It's what everything in Web3 has been built around. They don't want to be tied to any government regulation or any kind of entity. They don't want to be part of the G20. They don't want to be any of that. And some of this is changing, by the way, because people see now, I say adults in the room, see some value in actually being protected by governments and some regulation. But in general, a decentralized autonomous organization is member-directed community, not centralized leadership, used for any purpose. Usually there's voting or voting rights or some sort of share rights associated. And very much aligned with Bitcoin's original goal to eliminate to the need of mutually acceptable trust. You just have to trust the code. But blockchain code can be changed by the blockchain's governance. I haven't really heard too many people loudly say that because Jamie Dimon is the only one who's JP Morgan Chase said, don't be surprised if there's more than 21. Hey, it's the only person in the past year and a half that I've heard actually say that, but everybody knows it. Everybody actually part of that governance does it. So the implication is layer 1 cryptocurrency DAOs, governance rules. We can talk about layer 2 side chains. That's another talk that goes along. Or crypto holdings via a Web 2 provider like FTX requires a significant amount of user trust. Just don't invest your money without knowing who these people are, who they're governed by, what kind of protections and insurance that they have, and if that's okay with you. Lloyd's of London is not the federal government, but it is pretty good. By participating, you're agreeing to the terms of caveat emptor. So let me just close with what it is that I've attempted to convey today. You've learned a little bit about blockchains, databases, cryptocurrency fundamentals, and blockchain misconceptions. You learned about cryptographic hash functions and random number generators. Most importantly, you learned about every field and header of a Bitcoin version 2. And you've learned a little bit to get dangerous during virtual machine or contract code. We learned about consensus algorithms. We learned about the incredible ways of all proof of work blockchains. It's just crazy to me. It's not solving a puzzle. There's nothing glorious about that. It's a complete waste of energy. And you, as young people who are protecting the planet, hopefully for future generations, should be very much concerned about that. We've debunked some widely held beliefs about crypto supply. I talked about regulation. But the thing here is that these three things, the tools that you need to understand crypto, how blockchains work, and what these consensus algorithms are, how they're constructed, you now know probably better than 98% of the crazies that write journalistic stuff about Bitcoin, about Ethereum, about how it works, about supply, about solving a cryptographic puzzle. So with that, I think I'm done. If you could entertain any questions for me, I'll repeat them for the local people that are only picking it up from the ceiling mics.